So till now we saw basically the foundation of what LLM is and how it has generated, but now we are going to dive into like fine tuning and other topics, including tomorrow. So our next speaker is Ronnie, and he's going to talk about parameter efficient fine tuning in LLMs.
Thank you. So yeah, my name is Ronnie Paul. Thank you for coming to this session. I'm going to talk about parameter efficient fine tuning and its application. I'm currently pursuing my master's in AI model compression, but yeah, I'm excited to talk about this topic right here. So this is the outline for today for my presentation. I'm going to start off by giving you an introduction into what fine tuning is, the basics, and also to give you some sort of ground structure before we're moving into the core topic of the session, which is parameter efficient fine tuning, which is one of three approaches. There are two others. I'm going to compare them, or not compare, I'm going to describe them. And finally, I'm also going to do a showcase of an LLM fine tuner real-time application. So this is exciting. Yeah, so what is fine tuning? Let me start with the basic question here. So fine tuning is essentially taking a pre-trained model. And what I mean by a pre-trained model is you're taking an already configured, already adjusted, already optimized model from someone, and you're taking that model, which is specific to one task, by the way, and you're readjusting it and modifying at least one model parameter to be more specific to our use cases. I'm going to give you an example of what I mean by that. So we can take this base model as an example of analogy or representation of this ruby coming straight out of the earth. As we can see, the ruby is really rough around the edges. And even though it has its value, it's not really practical in our cases. So what we want to do is to take this ruby and we want to transform it into becoming more practical for our use cases. Maybe that is to be fit inside a ring or to be fit inside an applet. So to give you an even more concrete example of what I mean, we can take this base model right here. And if we were to type in, tell me how to fine tune a model, we would get something in response like, how can I control the complexity of the model? How do I know when my model is done? All of these key questions. And even though that's helpful, it's not really what we want in our response. We want something that is more practical. So we can take this and we can transform it, and we can get this fine-tuned model, Text DaVinci 003. And if we were to type in the exact same questions, tell me how to fine-tune a model. Fine-tuning a model involves adjusting the parameters of a pre-trained model in order to make it better suited for a given task. There are generally 3 steps into fine-tuning: select the base model, adjust the parameters, and train the model. So this is really something that we want more in a response. Now, having said that, why should we fine-tune? And if you look at the end results, comparing the training from scratch and also fine-tune, it doesn't really make any difference. But the process of actually getting to the fine-tune or getting to the model that we want really is significant. So training from scratch, first of all, it is very costly. It is really time-consuming. You have to do all of these experiments, testing with different architectures, testing with different, how many layers are you going to use? So you have to do a lot of testing, and this is going to be time-consuming. Now, with all of these experiments, it is also going to require a lot of computational hardware, computational complexity, and it also going to have to require a lot of a large data set, because now you're training all the weights from scratch. All of the weights are going to be initialized at random. So in order to optimize it, you really need to have a lot of samples. And you also have to answer for a lot of design questions, like what type of architecture are you going to use and how many layers are you going to use? So we can really see the power of fine-tuning. Now, having that said, there are mainly 3 options into tuning the parameters. We have what is called a full fine-tuning, in which you retrain all the parameters. And even though this is a robust approach, it's not really helpful in our cases because there might be plenty of parameters. And if we're going to readjust all of that, it's going to be costly. Now, having that said, might be useful in some cases. I'm working with model compression, and in model compression, we're basically, and sometimes we're removing some insignificant weights, and that may affect the overall architecture. So I'm using full fine tuning, but it's really inefficient. So we also got transfer learning, which basically frees all of the layers within the model, except for the last few heads. And the reason why we are freezing the base model is because the base models are generally going to be able to detect general features. For example, if we have a model that is going to classify cars, we generally want to freeze the base layer because these are going to detect general car features. So if you're going to fine-tune the model into predicting trucks instead, or classifying trucks, we generally want to keep the features that is going to detect general car vehicles like headlights and wheels and all of that kind of stuff. So parameter efficient fine-tuning, how does this differ? Well, even though we're freezing most of the layers in the transfer learning, now we're working on large language model. And like Abhinana said, she was basically predicting, or not predicting, we were basically saying that models these days have trillions of parameters, even though that's not been developed yet. But even with transfer learning, this is becoming really inefficient with this huge model. So we need a new technology to cope with that. And that's where we got parameter efficient fine-tuning. So there are mainly three categories into PEFT methods. PEFT stands for parameter efficient fine-tuning. These are additive, which will just augment or not augment, append some weights to the original foundation model. For example, we have soft prompting, which includes prompt tuning and also prefix tuning. There are several, by the way. I'm just including two of them. We also got reparameterization, which involves sort of breaking down the weight matrix to two smaller ones, for example, through a process of which is called decomposition. I'm going to go more into details about that later. And we also have selective, for example, bit fits. This will, for example, choose some layers to update the weights. So, for example, bitfill will only choose the biases, choose the bias to update. It has shown that it's not really effective in working with large language model. It only has proven to be effective working with smaller models. So for this reason, I'm not going to include it in this presentation, only the two first. Yeah, and as I said, there are several methods out there. I'm just including the prominent ones. So we have soft prompt tuning, which is an additive method. And to give you some context as to why soft prompt tuning is so effective, I'm going to describe what is generally done with this foundation model that we have. So we generally want to give the foundation model the most optimal full context possible, obviously because we want to receive the most optimal response. So this has generally been done by the use of prompt engineering, which will use hard prompts, and hard prompts are manually handcrafted prompts with human intervention. This may look something like this. Here's an example. Our prompt or our task is to translate from English to Norwegian, and then we provide some samples to make the model, to give the model the full context into understanding what we want in the response. So I provided just two samples, but obviously we would need a lot more. For example, butter equals to smør, king is equals to kong in Norwegian, and then we would finally put our request, which is to translate crazy. Now, the problem with prompt engineering is that, first of all, it is error prone. So there might be a lot of error in the model. No, not in the input embedding vectors. And also it is labor intensive. So this is why prompt tuning is so efficient, because it basically removes those. It will generally work by having a smaller model on top of the pre-trained model, hence why it's called additive, because you're adding a smaller model. And this model will generate what is called soft prompts, which are pre-appended to the input embedding vectors. So these may look something like this. Here we have these virtual tokens. And these are, by the way, not readable by the human eye, but these are pre-appended to the input embedding vectors. And these are also optimized. These are fine-tuned. Now, since we have soft prompt tuning, we could give the full context into the input embedded vectors, and we could also remove the labor intensive and the error prone aspect of hard prompts. So that is soft prompt tuning, and we also got prefix tuning, which is really similar to prompt tuning. The only difference is that we're working with prefixes, and prefixes contains the soft prompts, as I said, and the prefixes are task specific, and we can add several of these prefixes, meaning that we could have several tasks in a model architecture. And these are also not added to the input embedded vectors, but rather in the transformer block, which is basically like the building blocks of each. Yeah, the other question.
Can I ask a question? What do you mean by task specific?
Task specific?
Can you give an example?
Yeah, so this right here was a task specific. So we might want to fine tune a base model into becoming task specific to our problem. Like I said with the example I gave with the Ruby, like the Ruby was coming straight out of the earth was really general. We want to make it task specific in our practical use cases.
Task specific or industry specific, for example, if you want to build a model which works for economy section, then they have to be trained for economy related tasks.
Exactly. Yeah.
And that is why you will find it.
Exactly. So yeah, we may have several of these task specific, and it's really nice because we can just swap between these prefixes, meaning we could change the task. Okay, so now we have low ranking adaptation. And to describe the terms here, rank of a matrix is simply the number of linearly independent number of rows and columns within a matrix. And a low rank matrix is when you got when you're working with rank number of a matrix that is significantly smaller than the number of rows and columns within a given matrix. It's complicated, but what this essentially means is that when we're working with a low rank matrix, we're generally able to cap a very large complex of information within a given matrix, and we can represent it as this compact matrix. So it's compactable. With that being said, this research paper made by Facebook, this one right there, said that it is common for pre-trained models to have low intrinsic dimensions within a pre-trained model. So this means there's a lot of information within the model. It's commonly known that there's a lot of information within a model, and we can accurately represent this huge model in a relatively compact manner. So yeah, having that said, the developers of low-rank adaptation has taken a step further from this research paper. They're saying there's not only low intrinsic dimensions within the within the pre-trained model, there's also low intrinsic dimensions in the weight during adaptation. We're basically saying there's a lot of redundancy, there's a lot of information within this weight matrix during adaptation, and we can accurately represent this very huge weight matrix into two smaller ones during a process of matrix decomposition. So given that the rank is small, which we suggest, so for example, to give you an exact number on what I mean, if we were to say the dimension of this huge matrix was 1,000, both of them, 1,000 equals to 1 million parameters. And even though this might not seem like a lot within a matrix, it really can explode when you're stacking up these weights matrices and all these layers together. So it can really be significant. Now, if the rank were to be, for example, 2, then we would have 1,000 times 2, which equals to 2,000. And since we have 2 of them, it equals to 4,000. So now we're working with 4,000 trainable parameters as opposed to working with 1 million, which really makes a difference when you're fine-tuning.